Tonight we are going to talk about a star that went completely bonkers. Those are not my words. That is how the lead astronomer on this discovery described what he saw when he looked at the data. A star 11,000 light-years away. A star that had been sitting quietly and predictably in archival telescope records for years, emitting a steady, reliable beam of light, exactly as a sun-like star is supposed to. And then, starting in 2016, it began to do something that sun-like stars simply do not do. It began to flicker. 3 distinct dips in brightness, each one unexplained. And then, in 2021, the steady signal vanished entirely, replaced by wild, chaotic fluctuations that defied every standard explanation. Anastasios Zanadakis, a doctoral candidate at the University of Washington, was the person who found this. He was not looking for anything dramatic. He was reviewing archived telescope observations, the kind of methodical data archaeology that produces most of science's quieter discoveries. Thousands of light curves, thousands of flat lines representing thousands of stars behaving exactly as expected. And then one line that was not flat. One star that had departed from everything a star of its type should do. He pulled in his senior colleague, James Davenport. They looked at the data together. They had no explanation. What they eventually figured out was published on March 11th, 2026 in the astrophysical journal Letters. They had caught 2 planets destroying each other in real time. And the wreckage of that collision looks almost identical to the wreckage that created the Earth and the Moon 4.5 billion years ago. Let us start with why the star's behavior was so alarming. Gaia 20EHK is a main sequence star, meaning it is in the stable middle phase of its life, fusing hydrogen, emitting predictable light, behaving the way the Sun behaves. Main sequence stars are the universe's most reliable objects. They do not flicker. They do not go bonkers. Their light output is flat and consistent across years and decades of observation. When one starts flickering, it is not misbehaving. It is telling you something is getting between it and your telescope. Astronomers read starlight the way a doctor reads a pulse. The technique of detecting objects by the shadows they cast is the same method used to discover thousands of exoplanets. When a planet transits its star from our viewing angle, the star dims in a clean, repeating pattern. Same depth, same duration, same interval. The planet is there, the planet moves past, the light recovers, the cycle repeats. It is one of the most elegant methods in observational science. You never see the planet directly. You see the planet's shadow. What Gaia 20EHK was doing was nothing like that. The initial dips in 2016 were irregular, different depths, different durations. Not the clean signal of a stable orbit, but the messy signal of something chaotic. Like the difference between a metronome and someone drumming with their hands on a table. You can hear that something is happening. You cannot predict when the next beat will come or how loud it will be. And the 2021 chaos was more extreme still. The light flickering wildly, as if enormous quantities of constantly shifting material were crossing the star's face without any pattern at all. Zanadakis and Davenport ruled out everything ordinary. A comet cloud, an asteroid disk, an unusual stellar companion. Each hypothesis died on contact with some part of the evidence it could not account for. The case was genuinely unsolved for a period, until Davenport suggested looking at the system in a different kind of light entirely. Infrared light is heat. Cold dust blocking a star would dim its visible light without significantly brightening in the infrared. It is just passively blocking, the way a curtain blocks sunlight without generating any warmth of its own. But if the material were hot, genuinely hot, freshly generated hot, It would glow in the infrared even as it dimmed the visible light. The two signals would be mirror images of each other. That is exactly what they found. Now, as the visible light from Gaia 20 EHK flickered and dimmed, the infrared spiked. The team measured the debris temperature at around 900 Kelvin. The material blocking the star was not cold, ancient dust. It was freshly vaporized planetary rock. Something had been very recently, very violently destroyed. The reconstruction of events that followed is almost cinematic. Two planets had been spiraling toward each other over years. The three early dips in 2016 were grazing impacts, close passes that knocked material loose and sent debris clouds across the star's face. Not the catastrophic collision yet, just the opening acts. Then, in 2021, the planets finally hit each other for real. Two substantial worlds converting their mass and momentum into heat and shattered rock on a timescale effectively instantaneous by astronomical standards, in temperatures comparable to the surface of a star. Geological histories built over millions of years, obliterated in moments. What remained was a vast cloud of superheated wreckage orbiting the star in the irregular, chaotic pattern that the data had been showing all along. Now, here is something important to understand about why this discovery is as significant as it is. Planetary collisions are not rare in the universe. They are an absolutely standard part of how solar systems form. Every rocky planet that exists anywhere is the product of smaller bodies crashing together and merging under gravity. The Earth itself is an accumulation of collisions. But witnessing a planetary collision from Earth is extraordinarily rare because the requirements for detection are so specific that the odds of all of them being satisfied simultaneously for any given event are vanishingly small. The colliding planets have to be in a system oriented so that the debris passes directly across the face of the host star from our viewing angle. The debris cloud has to be large enough and dense enough to produce a detectable dimming signal. The collision has to happen at a time when telescopes are already collecting data on that star system, or have recently been collecting data so that the before and after are captured. And the signal has to be distinctive enough to be recognized as a collision rather than dismissed as an instrument artifact or an unusual but mundane stellar variable. Before Gaia 20 EHK, only a handful of planetary collision candidates had ever been identified across all of observational astronomy. A small number of events around other stars where infrared excess or unusual dust signatures suggested something violent had occurred, but none with the combination of visible light dimming, infrared brightening, temporal detail showing the progression from grazing impacts to catastrophic collision, and orbital positioning so directly analogous to our own solar system. Gaia 20 EHK is not just a rare event. It is the clearest and most detailed real-time observation of a planetary collision in the history of the field. Now here is where the story becomes something more than a remarkable observation. The debris cloud around Gaia 20 EHK orbits its star at approximately 1 astronomical unit. That is the distance between the Earth and the Sun. The debris from this planetary catastrophe is sitting in the same orbital zone as our own planet. At that distance, under similar heating from a similar star, the physics of what happens next are analogous to what happened in our own solar system 4.5 billion years ago. The giant impact hypothesis is the leading explanation for the origin of the Moon. Early in the solar system's violent youth, a Mars-sized body called Theia struck the young Earth in an oblique collision powerful enough to strip away a significant portion of the planet's outer layers and throw them into orbit. That orbiting debris, superheated and glowing, cooled and coalesced under gravity into the Moon. Some models suggest the process took as little as days or months. and a body the size of our moon, assembled from the wreckage of a planetary catastrophe in geological time that is almost nothing at all. The forensic evidence for this event is substantial. The moon's composition matches Earth's mantle rather than its core, consistent with material stripped from the outer layers in a glancing blow rather than a direct impact that would have mixed everything together. The moon has almost no iron core, consistent with the debris coming from the surface rather than the deep interior where iron accumulated early in Earth's history. Isotopic ratios in lunar rocks, the specific fingerprints of particular elements, match Earth's in ways that are extraordinarily difficult to explain by any formation model other than a giant impact with a body that had a similar chemical history. But the giant impact has always been a hypothesis built from backward inference. We had the outcome, the moon, and we were working toward the event. We had no direct observation of a comparable impact happening anywhere else. One data point, our own solar system. And one data point is not enough to know whether what happened to us was ordinary or exceptional. Gaia 20 EHK is potentially giving us a second. The parallels are explicit in the paper, the debris orbiting at 1 astronomical unit. The pattern of grazing impacts before the final catastrophic blow, mirroring the models of Theia's approach to Earth. The temperature and scale of the debris consistent with a collision between substantial planetary bodies rather than smaller asteroids. The authors are careful. They describe this as a likely planetary collision afterglow, a system that resembles the aftermath of a giant impact. Confirmation requires continued observation. The James Webb Space Telescope is well positioned to track how the debris evolves, but the convergence of independent evidence points in one direction clearly enough to publish and to take seriously. Here is why this matters beyond the spectacle of two worlds ending. The moon is not simply a decorative object in the night sky. Its gravitational influence stabilizes the tilt of Earth's axis, preventing the wild climatic swings that would make the surface far less predictable. Without the moon, the Earth's axial tilt could vary chaotically between near zero and extreme values over millions of years, producing ice ages and heat epochs on timescales too fast for complex ecosystems to adapt. The ocean tides driven by the moon mix chemistry globally, creating conditions in which early biology could experiment across coastlines and tidal pools. The moon may even play a role in plate tectonics, the geological engine that recycles carbon and keeps the planet's atmospheric chemistry in the long-term balance life depends on. Take the moon away from the Earth's history, and you do not simply get a planet without a large natural satellite. You potentially get a planet where complex multicellular life never gained sufficient stability to persist long enough to develop intelligence. The specific history of life on Earth may be inseparable from the specific violence that created the moon. Which means the question of how common the giant impact is may be the same question as how common we are. For most of scientific history, that question had no empirical path toward an answer. We could model it. We could theorize about collision rates in young solar systems, but we could not observe it. We had one example and no way to know if that example was typical or extraordinary. That is about to change dramatically. Davenport estimates that the Vera C. Rubin Observatory, beginning its legacy survey of space and time later this year, could detect as many as 100 similar impacts over the next decade. To understand what that means, consider what the Rubin Observatory actually is. It is a telescope in Chile with a mirror 8.5 meters across and a camera with over 3 billion pixels, the largest digital camera ever built for astronomical use. Its field of view is so wide that it can photograph an area of sky equivalent to 40 full moons in a single exposure. And its survey strategy involves photographing the entire southern sky repeatedly, returning to every patch every few nights, building up a time-lapse record of the universe at a scale that has never been attempted before. That time-lapse capability is precisely what planetary collision detection requires. You need to catch a star before, during, and after the event. You need the temporal detail that shows the progression from ordinary behavior to chaotic flickering. The Rubin Observatory will be generating that kind of data for millions of stars simultaneously. If planetary collisions like Gaia 20 EHK are occurring anywhere in the survey footprint, the Rubin Observatory has a genuine chance of catching them. 100 events over 10 years would transform this field from anecdote to statistics. We would start to know how common moon-forming impacts are. We would start to know whether the violence that made complex life possible on Earth is routine or exceptional. That answer has implications for the search for life beyond our solar system that are difficult to overstate. We looked at a flickering light 11,000 light-years away and found the wreckage of 2 worlds. In that wreckage, we found a mirror of our own origin, the same orbital distance, the same pattern of approach and impact, the same superheated debris cooling into an orbit where a new world might eventually form, though it may take a few million years to know what that world looks like. The discovery was not made by a grand program aimed at this specific question. It was made by a doctoral student reviewing old data who noticed a flat line that stopped being flat. He was not looking for the birth of a moon. He was not searching for a planetary catastrophe. He was doing the patient work of looking carefully at things the universe had already done and left the records of, waiting for the moment when one of those records turned out to be something extraordinary. We are the first generation in the history of this species to have watched something like the birth of the moon happen somewhere else. Not in our solar system, not to planets we will ever reach or rocks we will ever hold. 11,000 light-years away, to worlds that no longer exist, in a corner of the galaxy that was going about its violent, ordinary business, completely indifferent to the fact that someone was watching. But someone was watching. And in that watching, in that patient attention to a star that went completely bonkers, is something that science does at its best. It does not wait for the universe to announce its most important moments. It builds instruments and reviews data and notices anomalies and follows them wherever they lead. Sometimes they lead nowhere, and sometimes they lead to the wreckage of 2 worlds that ended so that we might understand how our own world began. Good night.